consecutive, but indeed they are not stored at contiguous location in the memory. So this is very important. Like with arrays, as you remember, arrays are consecutive memories, like the memory is consecutively located for arrays. Meaning, once you reach to arrays element I plus 1 is just next to element I in arrays. However, we don't know about the memory locations for linked list elements. Meaning, once you try to reach two consecutive elements, one might be at the beginning of the memory and the other one can be at the end of the memory. We don't have any guarantees about their continuity. So, elements are linked using pointers. Since they are not contiguous in the memory, we have to link them somehow, right? So we do this by the help of pointers. Like if you look at the example here, we usually represent and pass our linked list with their head. Like basically, head is a pointer to the beginning of the list, as we see here. And then at each node, usually you have the data section, which can be an integer, which can be an object, like it can be anything depending on your use cases. Also, each of the nodes of the linked list also have a next pointer that is used to link this element with the following element in the list. And in the end, usually your last element's next points to null. The reason is you need to know somehow your link is finished once you process your last element. That's why it's a good practice to initialize things with, like for example, in case of pointers, initialize them with null value so that we can distinguish the ones that are meaningful from the ones that are not used yet. Because if you let it have a random value, how are you going to distinguish a normal valid next pointer from a random pointer that is just pointing anywhere in the memory? Obviously, you don't have a nice way to distinguish them. That's why it is better to initialize them with null in case you don't use them. So in this case, you are going to make use of the next pointers for the first element, for the second element, and for the third element of the linked list. But when it comes to the last element of the, they don't have dynamic size. We cannot make it larger or make it smaller if we are defining a static array. But when it comes to linked list, it is very easy to expand or shrink the list. Like depending on the demand, we can make it longer by adding more and more nodes. And if we do not make use of these nodes, we can make it shorter by removing some. So it's unlike arrays, it has dynamic size. Secondly, it is actually related with the first one. It is easy to insert and delete elements to linked list. Once we say insert and delete, don't think of this as writing a value into cell of an array. Like basically for the array, we do not make any inserts or deletes. Like we manipulate the data that is inside of the array when we are writing something into cells or when we replace them with zero value or whatever. But the values are there. So for the array, there is no insert or delete operation that we do. And once you think about it, even logically speaking, once we are trying to insert an element between two elements in an array, what we have to do is we have to move all the elements that is right of the new element one right position, right? Like everything has to be moved so that we can insert a new element to array. Like let's see this with an example. I think it's going to be more clear. Let's say this is our array, and it has 6 elements. And initially, let's say we had 1, 2, 4, 5, 6, 7. 4, 5, 6. Let's say we don't have any element in the last position. And we want to insert 3 between 2 and 4. So what we are supposed to do is we have to move all these elements one by one to the next locations so that we make a room for 3. we can place 3 here, right? So as you see, inserting an element into an array can cost up to O. Yes, ON. But when it comes to linked list, this is actually not the case. Like in order to insert an element, after basically finding the right location, but it can be tricky to get to the right location, it is costly, you will see. But after that, inserting a new element, it's just creating a new node, and then pointing to the remaining part of the list with the new node. And then like basically, let's see, we want to do the same thing with linked list. So we have our head that is pointing to the first node of the list. We had one more, right? Okay. So at the beginning, our list was 1, 2, 4, 5, 6. And then we want to insert 3. So what we are going to do is we are going to create a node. We are going to write 3 inside. And then we will move from our head to the point where we want to insert a new element to the list. So we get to here. And then first, what we are going to do is we are going to make our new node point the previous next of the element that we want to insert the new element after. Like first we need to point here, because if we start pointing 3 directly from here, then we are going to lose our reference to this cell. Okay? So this is important. So that's why when we are introducing a new node to the linked list, what we are doing is first we are pointing with the new guy to the previous next of the node that we want to insert the new element after. So here 3 starts pointing 4. And then now we can safely update this pointer and then point 3. So as you see, instead of moving all the elements that is after the new element, we can easily insert a new element to the linked list after we get to the right point. And obviously it comes with some disadvantages. So since arrays are consecutive memories, we actually have random access, right? You can reach to array's ith element with ease. You just say array I and then it's available. But when it comes to linked lists, it's not easy to make random access. Like as you see, we define the linked list by its head. And if you want the ith element in the linked list, what you have to do is you have to travel starting from the beginning of the list and keep going till the ith element. So random access comes with costs. It's not like they are unreachable. No, we can reach, obviously. If we cannot reach, then why would we have that memory, right? They are reachable, however, reaching is costly. So reaching a random element, it takes ON time in linked list. Secondly, we are using extra memory, right? Like if you look at each node in the linked list, in order to keep data, we have to keep next pointer as well. So depending on the space of your data, it might be negligible. Let's say if your data is 20 megabytes, then having one pointer, you can safely ignore that cost, right? But if your data is just one integer, actually your pointer is as costly as your data. So you should keep it in mind. It comes with this additional cost. And lastly, they are not cache friendly. The reason is the elements of the linked list, they are not kept consecutively in the memory, right? So if you want to reach the second element after the first one, there is no guarantee that it's going to be in the cache. If you want to reach the third element after the second one, this can be at the completely other end of the memory. So not necessarily it's going to be in the cache. That's why it is not cache friendly. But when it comes to arrays, since they are consecutive in the memory, they are very cache friendly. Once you reach to the ith element, you can assume that I plus 1 is going to be in the cache. Because as you know, like the data is read in chunk. It is brought in chunks to the memory. So once you make access to one cell, then the consecutive cells are going to be brought to the cache as well. That's why you are going to have fast access. But when it comes to linked list, you don't have this advantage anymore because the memory is not consecutive. So, what are nodes? Like as we said, linked lists consist of nodes. Node is the basic data structure that we are using to create linked lists. So each element is called node basically. And first node is conventionally called head of the linked list. And this is how we reference to linked lists and how we pass them from one function to another, or how we reference them. Head is very important for linked lists for that reason. So let's look at the node implementations in different languages. It's actually pretty simple. Like in C, we are going to represent them with structs. Structs are like classes in C, since you don't have classes. Like it's used to package different types of data. And here, like the int type for data, it's just an example. So it can be any type depending on your purposes. It can be your class as well, or another struct. And secondly, you have a pointer that is pointing to nodes, like another types of nodes basically. Because in the linked list, it consists of nodes, right? So each pointer is actually pointing either null or another node. So in C++, it's very similar. So this time instead of struct, you can define it with class. I mean, you can also define it with struct. There is nothing that is preventing you not to use structs, but you can represent it with class. And again, it's very similar. You have a node pointer, meaning a pointer that is pointing to a node object. And in Java, again, the idea is very similar. So instead of having pointers, this time you have reference. So your next is referencing to another node object. And likewise, in Python, you have the data part, and you have the next pointer. So here, it is initialized to null when you are creating it. But obviously, if you want to create a meaningful list, as you insert new elements, you need to manipulate the next element so that your linked list is still connected. So that's it for the linked list. And we are going to do some examples of linked lists in this today's session. Lastly, the reason we are covering linked lists is not because linked lists are super useful, but this structure can be developed and some new fields can be added, and after that it can convert. We can convert it to a binary tree. We can convert it to trie. So many advanced data structures that are super useful, super handy solving complex tasks. Their logic is actually diverse from the logic of linked lists. So that's why it is very essential. That's why it is important to get comfortable implementing linked lists, making some manipulation like adding an element to between, removing random elements, getting familiar with using references and pointers depending on what language you are using. So that's why we are starting with the easy version, okay? Because rather than that, I don't think like you will ever have to implement your own linked list in your professional career. But you might have to implement your own tree. You might have to implement your own trie. Like also in competitive programming, a lot of questions are going to require that kind of advanced data structures. So that's why it's important to have our foundation strong and make ourselves familiar with this simple but in the long run can turn into be powerful data structure. Any questions so far? All right, so in that case, let's continue with exercise session. And I'm going to be adding more questions now.